Welcome back. In this session of memory interfacing, we will be covering the rest of 16-bit interfacing of memory to 8086. As we have seen in the last class, 8086 can access 1 mega address range due to the 20 address lines A0 to A19, and if you have to interface a memory, either a RAM or ROM, to one of these ranges in this 1 megabyte, we have to use decoding or memory interfacing circuitry. The memory interfacing circuitry generally is of two types. One is through the logic gates and the other is through the decoder. The one through the logic gates, what does it do? We require, let us say I have a RAM. The RAM requires A0 to A6, then A0 to A6 is connected directly. The rest of the bits, address bits A7 to A19 are decoded and fed to the chip select. So this is an example wherein we have 32K into 8 RAM. So for 32K we need 15 address lines, that is 32 is 2 power 5 into 2 power 10, and the 15 address lines are A0 to A14 and they are fed directly to the 8086 address lines. The remaining higher address lines A15 to A19 are decoded through the NAND gate. For this combination, let us say A19 is 1, 18 is 1, 17 is 0, 16 is 1 and 15 equal to 0. That is 1, 1, 0, 1, 0. This NAND gate output becomes low and CS gets activated. So based on this we define the memory map, and clubbing 4 bits together we get the address range as D4 zeros to D7FF, that is the start and end address. This we have seen in last class in detail. So, the next type of decoding is through a decoder. Instead of using 1 NAND gate for each memory chip, and if these memory chips are assigned contiguous memory addresses, we can use a decoder. And in this example of 3:8 decoder, we have seen Y4 being activated due to these combinations of 1100. That is A19 is given to G, G is active high, G2 active low, they are permanently low. Then we have the rest A18 to A16, they are all 001, that is Y4 gets activated. So the range we have seen as C4 zeros to C4 Fs. We had another combination, this was your homework. Here we had a higher ROM, that is 16K ROM. Previously we had 64K ROM. Here we had a 16K ROM. So this used address lines of only A0 to A13, that is 14 address lines, and the remaining address lines we had checked it here itself. So we had accommodated here only. So A14 to A19, A19 we gave it to G1, G2 are active low, so A17 and A18 should become low here to enable. So if they are 1, 1, these G2s gets enabled. Then A14 and A16 combination, they select your one of your Ys. So your ABC is nothing but A14, A15, A16, the green color ones here, and for Y4 these are 100. If I want Y1, this will be 001 and so on. Then what about A19, A18 and A17? A19 active high 1, A18 and 17 through an inverter they are given, so there should be 1, 1, so that here at G2 they will be 0 and this gets activated. As usual, the start range is all zeros and the end range is all ones of the 16K ROM. So we have the range for Y4 for this combination as F4 zeros to F3 Fs. So look here, this is your F and this is 0011 is 3 and the rest are FF. The extend this application for Y3 instead of Y4. If I connect another chip at Y3, the range will be CBA will be 011 and this address range is EC00 to EFF. You can also verify for Wi-Fi and so on. Now coming back to this data lines interfacing. Until now we were worried about only address lines and decoding of the address lines to select the chips. What about the data? The data here we have seen that it is D0 to D7, 16K into 8. 16K into 8 gives the organization. Here we have 8 address lines. So when I have like this 32K into 8, once again you have an 8 address lines, and these 8 data lines, and the 8 data lines are D0 to D7. Using these data lines we can read and write from the memory. What about the address lines A0 to A14? This address decoding we have done in last class, and we have just revised now, that is using NAND gates and decoder. And how is the data stored in this memory? You have n memory locations, 2 power k memory locations. Each location will contain 8-bit data because it is 32K into 8. So let us say in one location it has data 1, next location data 2, and so on. The size of each data here is 8 bits. Instead of a byte data, if you have a word data, let us say a 16-bit word data, the 16-bit word data is D0 to D15. It consists of 2 bytes, and the 2 bytes I'll specify as one as lower byte. This is also known as LSB, lower significant byte, and then you also have an upper byte. And these two bytes, if they have to be stored in memory, the convention is first the lower byte is stored and then the upper byte. Let us say lower byte is stored at 8000 address, then what about the upper byte? The next consecutive location will have the upper byte. So once you have finished one word, then the next word is stored. The LB2 and UB2 correspond to the next 16-bit word. To access this, to access these data, what does a 8086 processor do? First it puts the address 8000, gets the LB1, then it will increment the address to 8001, get UB1. So the amount of time taken to read one word will be 2 cycles. 2 times it has to access. Each time it has to change the address. The best would have been if we had 32K into 16 RAM. If we had 32K into 16 RAM, each location I can have a 16-bit word, and every time I put an address I get 16 bits of the word at a time. But this is not in practice. When we look at the conventional RAM chips available, all of them are cross 8s, that is 2K into 8 or 8K into 8. There will be of lower configuration also, 16K into 1. All these your DRAMs are all 111, and whereas SRAMs are also 8. Some are across 4, that is nibbles also. So the data sizes of the memory chips are 1 bit per location, or 4 bits per location, or 8 bits per location. 16 bits per location is quite rare. Similarly, in ROM memory chips, here also we can see that all of them are almost byte locations. Each memory location contains 8 bits of data. So one way to access a word is this technique of dividing, of using 2 memory banks or 2 memory chips. One memory chip we will designate as even bank, the other memory chip we will designate as the odd bank. And in one bank we will store all the lower addresses, that is LB1, the lower bytes, and in the other ones we will store all the upper bytes. For example, the first location here, 8000, will store the lower byte of word 1, whereas 8001 will have the upper byte. Similarly, 8002 and 3 together corresponds to the word 2, and so on. And if we have to store a 32-bit word, instead of 2 banks, we can increase it to 4 banks. 4 chips will be accessed at the same time, so I get 4 bytes of data. Why do we require 4 bytes of data? 32 bits, you can have the data as D0 to D31. You can split it up as 4 bytes. Byte 0 is D0 to D7, 8-bit data. Another 8-bit data is D8 to D15, then D16 to D23, and so on. So we have 4 bytes of data, and all these 4 bytes of data together is a 32-bit word. So if my data bus is 32-bit, if the processor, then I can access from 4 memory chips. Each memory chip is holding 1 byte of data, and if 4 of them give me parallel 8-bit data, we get the 32-bit data. So in 8086 we have a 16-bit address line, 20-bit address line and 16-bit data lines. Now since we have a 16-bit data lines D0 to D7 and D8 to D15, we would like to access 16-bit data from the memory at once. To access the 16-bit data from the memory at once, these banks are enabled by A0 and BHE. There is one bus high enable BHE extra pin given, and this pin will enable the odd bank, and the even bank is enabled by A0 being 0. Suppose both of them are 0, 0, A0 is 0, BHE is 0, then both banks are enabled, and the data from the even bank is put on D0 to D7, and the data from the odd bank is put on D0 to, the D0 of D7 is put on D8 to D15. So at once I can read the data from D0 to D15, or 16-bit data you get at once. This is possible if both the pins BHE and A0 are 0, 0. In 8086, not only reading a word, you also have flexibility to choose 1 byte at a time. For example, move AL square brackets 4503. This square brackets 4503 implies contents from memory location 4503. Now this is an odd address. So now if it's an odd address, it means that it is stored in the odd bank, and you have to read from the odd bank. To read from the odd bank, BHE should be 0 and A0 should be 1. I don't need the even bank, so make BHE equal to 0. So the data from the odd address or bank or memory bank will be put on the data lines. The data lines are D8 to D15. We also have flexibility to read 1 byte of data from an even bank. For example, move CH. CH is an 8-bit register, and to this 8-bit register you are moving an 8-bit data from 5600. So 5600 is an even address, and since it's an even address, all even addresses are stored in the even bank, and you to activate this even bank, A0 is 0. And I don't need the odd bank, so BHE is equal to 1. So this flexibility is available by using the extra pin BHE equal to 0. I can read 1 byte at a time, and that 1 byte can be either from the odd or a even. And if you have to read 1 word at a time, and if the word is stored at an even address, I can activate both BHE and A0 at once and read the word. But if the word is at an odd address, then what will happen? So before we go, we'll just check what happens if the word is at an even address. So we make both BHE and A0 equal to 0, 0. So the lower byte is stored at the even address and the upper byte is stored at the next odd address. So 616 contains the lower byte and 617 contains the upper byte of the address. So when I activate both of them, how do we activate both of them? A19 to A1 along with A0 together represents FF616. So this will activate this bank, and with BHE equal to 0, A1 to A19 will activate this, and along with BHE the upper bank is also activated, and the complete 16-bit data is put on the 16-bit address lines. And what is the time required for this? This is 1 memory cycle. The time required to get 1 word of data, that is 16-bit of data, it is 1 memory cycle. What about if it is stored at the odd address? let us say move AX. AX specifies a 16-bit register. So from this memory location you are reading a 16-bit data. But to read the 16-bit data, the data is stored at an odd address. And we see that it takes 2 memory cycles. How does it take 2 memory cycles? Now let us see this. So when I have a data at an odd address, let us say 4503, at 4503 the lower byte is stored. The lower byte is stored at 4503, that comes in the odd bank. Then the next upper byte is in the next memory location. The next consecutive memory location is 4504, and 4504 comes in the even bank. Now if I put the address of 4503 here, so how is 4503 put here? So 4 expand along with A19 to A1 you expand, so we get 450, and this becomes 001 A1, A0 is 1, so this is 3. And what about BHE? BHE is 0. Because we are activating the odd bank. And with this combination, A0 equal to 1 and BHE equal to 0, and the rest A1 to A19 is equal to 4503, it will activate this address 4503, and the contents of this location, which contains the lower byte of data, is put on D7 to D0. In the next clock cycle, the address is changed for 4504. So for 4504, the address lines A19 to A4 remain the same, that is 0450. Here A3 also remains the same, but A2 will change from 0 to 1, and A1 1 to 0, and A0 from 1 to 0. So this reads 4. That is 100, that is 4. And what about your BHE? BHE is 1 because we are accessing the even bank. And when we are accessing even bank 4504, I don't need BHE. And this data 100 will give me the 4504. I get the upper byte of data. Together now this will read, but this data now will be put on D8 to D15. I cannot now, if the word is stored at an odd address, you cannot access both bytes at the same time. First you have to access the odd bank and then the even bank, so to get the upper byte. So it's better if I can store the word starting at an even address. To enable this, to store at an even address, we use a even directive. When you are writing an assembly language program, assigning the address is the job of the linker. To tell to the linker that we would like to have all the words stored on an even boundary, we can say, we can use the directive even. So after using the assembler directive even, whatever variable we give, here example value 1 is a variable, DW question mark is, it is just assigned, data is not put in it, previous data can continue. So value 1 is a 16-bit variable, and this variable will have an even address, and the following all will also have a even address. So this will ensure that all the words are located at an even boundary, so that if they are at an even boundary, it will take only one memory cycle. If you have at the odd bank, it takes double the time, it takes 2 memory cycles. And coming to the interfacing, how exactly is this interface? So you have the 2 banks here. So the 2 banks, this D0 to D7 and this D0 to D7. The even is generally connected to D0 to D7, and odd is connected to D8 to D15. So total 16-bit data you can get. What about the addresses? This A0 to A13. This is 16K into 8 ROM. So for this 16K, I need 14 address lines, and at 14 address lines are A0 to A13. And to the processor, from the processors, you don't get A0 to A13. A0 we have taken to select the banks, so remaining are A1 to A14. A1 to A14 you use it to select both the banks. Later, the higher address lines A15 to A19 are given to the chip select, So this is your chip select here, and this output of the chip select along with BHE will select CS1 for your odd bank, and the same chip select along with A0 will select CS2, that is a even bank. So together all these NAND gates can be put like this. This is your A15 to A19, and that along with BHE selects CS1, and the same chip select along with A0 will select CS2. So this is an extension of your memory mapping, wherein we are using A0 to select the even bank and BHE to select the odd bank, and the remaining address lines A1 to A15, A1 to A14 go to these two, both the banks, and the higher ones A15 to A19 go to the NAND gates. A slight change from whatever decoding circuitry we have studied with NAND and decoder. This enables 16-bit data transfer at once. Now, how do we quantify the speed of the processor? Because here we have taken 2 memory cycles and we are saying we would like to have only 1 memory cycle. We have to read it or access it faster. For this we have one quantity known as a bus bandwidth. The bus bandwidth is defined as 1 by bus cycle time into bus width in bytes. Now these are the 2 parameters, and if we can improve any one parameter, the bus bandwidth becomes better. What is the definition of bus bandwidth? The bus bandwidth is the rate of data transfer between CPU and the memory and peripherals. Remember, the memory and the IO peripherals are the outside world, and the CPU has to take the data from these and process. If I have a faster CPU and slower memory or slow peripherals, it is of no use, as the CPU requires the data from the memory or peripherals. Only after it gets the data from the memory and peripherals can it process. So if I can have faster data transfer from this memory and peripherals, the CPU's fast clock rate or the processing speed of CPU will be of much use. So the one that is the requirement of bus bandwidth. So for the bus bandwidth, that is the rate of data transfer should be as high as possible, and that should possibly match with the CPU processing time. And as we have seen, the bus bandwidth depends not only on the bus cycle time, it also depends on the bus width. Suppose the bus width is increased. We have just seen the bus widths being increased from 8 bits to 16 bits. So as soon as we increase from 8 bits to 16 bits, from 2 memory cycles, the time required has reduced to 1 memory cycle, and it has become faster. Similarly, the bus width can be still increased further from 16 bits in 8286 to 64 bits in Pentium. Remember, we have 8086 and 8286, 386, 486, Pentium, Celeron, and so on. So the bus width of 16 bits in 286 processor is increased to 64 bits in Pentium. As soon as the bus width in bytes, when I look at in the bytes, what happens to the bus bandwidth? So 16 bits is 2. So cycle time into 2 will now be increased to 2 into 8, so 4 time increase. And let us consider a typical CPU with speeds of 1 gigahertz or higher, and the bus cycle time for any memory device, because the memory has to communicate on some lines, memory lines on the PCB. The bus cycle time at present maximum is around 133 megahertz. And in older PCs, we had ISA slot. Now this ISA slot you was using still using large and bulky connectors, so it becomes noisier if I increase speed greater than 8 megahertz. So when I have an ISA slot, the ISA slot, when you open up your computer, in the end of the computer there are some slots. In these slots you put in your video graphics slots or cards or any daughter cards, and any peripherals. If you have to connect it to the computer, you connect through these slots. So if I use ISA slot, the maximum speed it can go is 8 megahertz, but the computer speed is 1 gigahertz, so the matching is very less. And if you have even a Pentium processor working at 500 megahertz, it should slow down to 8 megahertz when it is accessing the ISA bus. So one way to go around is use a better bus, that is PCI bus. In this PCI bus, the speed increases from 8 mega to 133 mega, and not only the speed increases, now if the speed increases, the 1 by bus cycle time becomes better, and the bus bandwidth also is increased from 16 to 64 bits. So with these two, the bus bandwidth will increase and they may approach the CPU speed of 1 gigahertz. So just recapping, so the bus bandwidth tells you about how fast the data transfer between CPU and the outside world, here memory and peripherals, can take place. So to increase this bus bandwidth, we have to increase either the bus width, that is possible with higher processors wherein you have increase from 16 bits to 64 bits, or increase the bus cycle time. But increasing the bus cycle time is difficult because it depends on the manufacturing of the memory devices and the slots in which these memory devices are connected. And if you use ISA slot, it is 8 megahertz, and if you use PCI bus, it is around 133 megahertz. Assuming that we are using 133 megahertz, and to increase this still further, we increase the data bus width to 64 bits and above. What happens if it is slower, if the memory is slower? Then we have to insert wait states. So what do you mean by wait states? Let us say as soon as in T1 cycle the CPU puts out the address and it is waiting for data from the memory. If the memory is ready, it will immediately put the data on the data bus. So here there are no wait states. But if the memory is slow, and the data is not available on the data bus, it has to wait one more clock cycle, and this clock cycle is known as the wait states. And if the memory is still slower, instead of 1 wait states, you may have to increase it to 2, 3, etc. So you can use wait states, or you can use another solution like faster memories like DRAMs or cache memory. These are the other techniques to access faster. So the simplest one is inserting wait states. So wait states are inserted between as soon as you put the address on the address bus, you wait till the data is available on the data bus. Now you have an example here wherein we compute the memory cycle time of a particular system, that is 8386 system, which is having a clock of 20 megahertz, and when I have 0 wait states, 1 or 2 wait states, what is the memory cycle time required? So first let us compute the clock period T. The clock period T is 1 by 20 mega. The 20 mega is here, mega is 10 power 6, and so that corresponds to 50 nanoseconds. So each clock time is 15 nanoseconds. The memory cycle time is with 0 wait states, as we need a minimum of 2 clock cycles. 1 clock cycle to put the address on the address bus, and another clock cycle to read the data from the data bus. So since if we have 2 clock cycles, what is the time taken? Time taken is 100 nanoseconds. Now let us assume that there is a 1 wait state inserted because the memory is slow. Then what will be the total time taken, or the what is the memory cycle time? This 2t plus 1 wait state. This 1 wait state is equivalent to 1 clock cycle. So totally it will take 3 clock cycles. So each clock cycle is 50 nanoseconds. So the 3t becomes 150 nanoseconds. As we have seen, the memory access time has increased from 100 nanoseconds to 150 nanoseconds, or the processing becomes slower. We'll increase it further. If the memory is still slower, instead of 1 wait states, if we have 2 wait states, then what is the total time taken? For 2t, it is 2t plus 2 wait states. 2 wait states is again 2 clock cycles. Total we have 4t, and 4t corresponds to 200 nanoseconds. And let us say I need 160 or 170 nanoseconds. That is not possible. The wait state that you are going to insert has to be an integer number. I cannot insert half a clock cycle or a quarter clock cycle. That is 1.25 t is not allowed. Either you have to use 1 t or the next integer 2 t. Generally the higher integer 2 t is used. Okay, now as we have seen, the delay in memory read is to two factors. One is the time taken for the address signals to go from CPU pins to memory pins. As soon as you put the address signals on the CPU pins, that is your 8086 address lines A0 to A19, it has to travel to the memory input pins, but while traveling it has to go through decoders, buffers, etc. and also from memory to CPU back. Again it has to travel through some more inverters and buffers, etc. So you have a path delay. So this whole thing is a path delay. And also you need in the memory, as soon as a address is available, as soon as it is enabled, the memory requires some time for the data in its location to put on the data bus. So this is this is larger among these two. So one is a path delay through the gates and the other is a memory access time to get the data out of the memory chips. Out of these two delays, the second one is higher and it depends on the type of memory that we use. So DRAMs are faster, wherein it is stored as charge on the capacitor compared to other SRAMs and ROMs. So I was talking about the latches and buffers. These are examples. Latches are used at the output port. Many a time we have multiplexed buses, that is your multiplexed pins. These are the multiplex pins on which we use both the address and data. So as soon as you put the address on the data pins, the address has to be latched into the latches. And once they are latched into the latches, the address will be fed to the ROMs here or RAMs or the memory chips. And once they are activated through the chip select, etc., the data has to be put on the data bus. So this data on the data bus, once again through the transceivers or buffers, it is fed into the latches. So it has to travel this, you put the address on the address lines, it has to go through the latches, the decoding circuitry, come to the memory. And the memory, once it is enabled, it requires some time, that is an access time, and after the access time it will put the data on this. And again the data has to go, this portion is your path delay and this portion is your memory access delay. So together so by the time the address is there and the data is present here, some delay is present. To compensate for the delay, we have the wait states. Okay, this example shows you the use of this buffers, that is 74LS245 from the memory. That as soon as the data is put, it's put on the transceiver here. In the transceiver you have the direction, you have a memory read, it will tell you that the data has to be read from D0 to D7. Suppose if this direction is reversed, the data will be written from CPU into the memory. Like this, for both the banks we have both the 1 transceiver. For every 8 bits you have one transceiver. Now this is a problem which tells us how to calculate the number of wait states. So let us say we have the same processor 8386 running with a 20 megahertz clock, and it is interfaced to a ROM, and the memory here is having 150 nanosecond speed. Now we have to calculate the number of wait states needed if the path delay is 25 nanoseconds. So in this example, here this ROM is 150 nanoseconds, it requires 150 nanoseconds. This path delay is 25 nanoseconds. So total delay is 25 plus 150. So the total delay here is 25 plus 150, that is 175 nanoseconds. So the clock speed, the CPU clock speed is 20 megahertz. So the cycle time is 50 nanoseconds. Generally, how much time do we need? 2T cycles. 2T cycles means without wait state 100 nanoseconds. This operation should be completed within 100 nanoseconds. But minimum delay that we have is 175 nanoseconds. nanoseconds. This 175 nanoseconds is greater than 100 nanoseconds. So since we cannot complete this 175 in 100 nanoseconds, the memory cycle time has to be increased by inserting wait states. So for 175 nanoseconds, suppose I insert one clock cycle, that one clock cycle is 50. So 100 plus 50, 150. That is still lesser than 175. So insert two clock cycles. So if I insert two clock cycles, that is 100 plus 100, 200 nanoseconds. And this 200 nanoseconds is greater than 175, and you can comfortably read the data from this ROM. So the ROM of 150 nanosecond speed is quite slow, which requires two wait states. The last portion that we are talking about is data integrity in RAM and ROM. So what do you mean by data integrity? So data integrity is you write some data into memory, and when you retrieve it, you should get the same data that you have stored. If this is so, then you say that data integrity is maintained. Or when we are transferring data from one place to another, whatever you have transferred, you should get or you should receive. So data integrity is used at two places, that is when you're stored in memory and you're reading it back, you should get the same data shouldn't be corrupted. The second place where we are using data integrity is when we are transferring data from one end to the other. So you have a lot of places where error can creep in. So to ensure data integrity, we have different methods. The first method is checksum byte. It's quite simple, and the checksum byte is generally used for ROM type of memory. The second is parity bit method, that is used for DRAM, and the third is cyclic redundancy check. This is your one which is used for mass storage devices like hard disk or internet data transfer, wherein you have a lot of data to be transmitted. So in this class we will be talking only about two methods, that is checksum byte method and parity bit method. So how do you do the checksum byte method? In the checksum byte method, it's nothing but an extra, the checksum byte is nothing but an extra byte which is tagged to the end of series of data bytes. What is its use? It will detect corruption of ROM contents. Why does this happen? Why does corruption happen? It may be a simple reason, like you have a current surge either when the PC is turned on or during operation, and this current surge may corrupt, that is a 1 may become a 0 or a 0 can become a 1. So how do we go about this checksum byte method? The steps are, first all the data bytes are added together, and during addition you drop the carries, and whatever total sum you get, it takes the 2's complement of that, and that itself is the checksum byte. And at the receiver end or during the storage, what do? We add all the bytes including the checksum byte, and the result should be 0. If it is 0, then there is no corruption. If any one of the bytes here has been corrected, one or more bytes, then the results will not be 0. That is, you add all the bytes including the checksum byte, you should get 0. If it is non-zero, it implies one or more bytes are corrupted. This we'll take with an example. So this is your checksum procedure. We'll come to it little later. Now let us say that I have 4 bytes of data, 25, 62, 3F, 52. So all these have been stored in memory. To this I add this checksum byte. How is a checksum byte? Add up all, you get 118. In this 118, drop the carry, take this 18H, and for this 18H performs 2's complement, and once we perform 2's complement of 18H, we get E8H. This E8H is a checksum byte, Then when we have to check whether this is correct or not, now what is stored? The same data is stored. Along with this data, the checksum byte is also stored. So the memory storage requirement increases, or redundancy is added to the data. Instead of storing 4 bytes of data, now we are storing 5 bytes of data. The 5th byte is E8H. When we are retrieving data, assume that one of the byte has changed. Instead of 62H, it has been corrupted to 22H. Now let us just check, add up all 25 with this 22, 3F, 52, 50, E8. What is E8? The checksum byte which has been added at the end. When we add up all this, I get 1C0H, and even if you drop that 1, the carry, the sum is not 0. Since the sum is not 0, it implies there is an error. To cross check, let us say this has not been corrected. So 25, 62 all are there as is, plus this checksum byte E8 you add, you get something like 200. Drop the carry 2, the 00 indicates that there is no error. So using the simple method wherein we add one extra byte at the end, that extra byte is a checksum byte. This is computed by adding all the data bytes and taking the 2's complement of the sum. So similarly, when we receive a series of data, this is your series of data bytes, and in the series of data bytes you also have the checksum byte. The job of the receiver is to just add all the bytes together. So here they receive some 10 or 12 bytes including the checksum bytes, and when we have added all the received bytes together and we get 500, just drop the 5, there's a carry, the total sum is 00. There's 00 indicates that there is no error in the received data bytes. Okay, so the checksum byte method can also be implemented in 886 program. So it's just a small procedure. So this is checksum procedure near. So move CX with the number of bytes to be added. Let us say here 8192. Then clear AL. Then to AL you get the data, the bytes, the first bytes from BX. BX is pointing to the table of bytes. So take the byte data, add it to AL, increment BX to point to the next data. So first BX will be pointing to 25, then get 25. After that increment BX to point to 62. So add that 62 also to AL. So you keep looping it till all the number of bytes, that the counter becomes 0, and afterwards what do we do? Or AL comma AL. AL contains the sum. By chance if AL is 0, if AL is 0, AL 0 with 0, when you or the 0 flag is set. If the 0 flag is set, it implies the sum is 0 and hence there is no error. If the 0 flag is not set, it implies that there is an error. So this is a simple checksum procedure wherein we check whether a corruption has happened or not. The next type, the second method, is a parity bit method, and this parity bit method is commonly used for checking DRAM error correction, that is in DRAM memories. Generally, two types of errors will occur in DRAM. They are hard and soft errors. Hard bit error is when some bits or an entire row of memory cells get stuck to either a high or low permanently. So whatever you write, whether you write a 1 or a 0, whatever it is stuck, even if you write a 0, if it is stuck at high, stuck at 1, it will remain at 1. So this is known as a hard bit error. Or another type, during any current search, etc., some single bits may change from 1 to 0 or 0 to 1. Whatever the types of errors, you can use this parity bit to at least check the error. And this is your possible memory configuration for 640K DRAM. To realize 640K, what we do is we take some banks of DRAMs. Here we have taken, so each DRAM is 64K into 4. So 64K into 4 means 64K locations, and each location is containing 4 bit of data. But if I require 1 byte, this 4 bit of data, so I need 2 banks. So 2 banks together gives me 8 bit of data. So one bank gives me D0 to D3, the next bank gives me D4 to D7. So total I get 8 bit of data. So 2 chips you use, DRAM, and this 64K into 4 and this 64K into 4 totally gives me 64K into 8. So that is totally 64K location, and total is 64K into 8. Let us, how many locations do I need? 64K, 64K, then 256, 256, add up. 256 plus 64K is something like 320, and again this is another 320, total 640. So we can have a 640K, and total will be, these are duplicated, so that into 4 becomes into 8, we have 8 bits. So along with this I have one more 64K into 1. So 64K locations, but each location contains 1 bit of data. So these banks are known as the parity banks. They hold only the parity bits. So these parity bits are added extra to, along with these 8 bits of data, 1 bit, that the 9th bit is added extra to check for parity bit. The parity bit helps in error correction. How does it help in error correction? So for the parity bit I require, let us say, a parity bit generator and checker. These 74280 is a parity bit generator and checker. It takes in 8 bits of data, that is A to H plus I. I is your extra parity bit, and if the inputs are A to H, 8 bit of data plus I, and it generates 2 outputs. One is even output and other is odd output. If A to H is even, that is even number of ones are there, and I is 0, then the total number of ones is even, and the even output will become 1. And what about odd output? We don't have odd number of ones, rather we have even number of ones, and A is also 0. Totally it is still even, so this becomes 1, and odd output becomes 0. Let us say A to H, on this 8-bit data A to H, when you count the number of ones, the number of ones count has become odd, and I is also 1. So totally let us say 3 ones are there, plus I is 1, totally 4 ones. 4 ones is again even number, so even will be 1 and odd continues to be 0. In the other two cases, so the total number of ones is 4, and what about I is also 1, so 4 plus 1 5. 5 is an odd number of ones. Since it's an odd number of ones, odd will be high and even is 0. And the last case, I have I is 0, but A to H has odd number of ones, let us say 1 or 5 or 7. So automatically this odd will become 1 because odd number of ones we have. So this is how this even parity checker works. Now we will use this here. So we use a parity checker, and we have the 64K into 1 DRAMs. So for 8 data, D0 to D7, for D0 to D7 we have so many banks. Each bank will be storing 1 bit. Along with D0 to D7 8 bit, we also have the parity bit at the end. So one more bank, so totally 9 bits. This is memory storage, and whatever memory is address lines are coming from the CPU, they are decoded through these latches, that is 74LS14. After decoding, they are fed to A0 to A7, and this will select the memory banks. So apart from the address that is known as MA0 to MA7, you also have the data. The data through the transceiver here, that is 7LS245, is fed to the 8 data pins here, D0 to D7, and along with the D0 to D7 of the data memory, it is also fed to this parity checker, that is 74280, A to H, and whatever is stored here, the parity bit is given through a NAND gate to this I, and also to the latch here, 7474 latch. Basically the setup consists of memory, 8-bit DRAM memory plus 1 parity checker. These address lines are decoded. Then we have the data lines, data to be written to given to the DRAM as well as to the parity checker. Now let us look at the operation. first one byte of data has to be returned to a DRAM location. So this D0 to D7 has to be written. To write, we have two signals, memory read and memory write. So for writing operation, memory write will become 0. So when memory write is 0, memory read is 1. So if memory read is 1, this becomes 0. So the output of this AND gate becomes 0. So I becomes 0. So I is 0. Why is I 0? Because memory read is 1. We are writing data into the memory. And now consider that we are writing a byte with even number of ones. So if you are writing a byte with even number of ones, that is on A to H you have even number of ones, and that is given to this 280. This will now at its input A to H, it is having even number of ones and I is 0. So total number of ones is even. So the even will go high, and the odd will go low. This even, you have the same memory right here, it will enable the tri-state buffer. So this is your tri-state buffer. So if it is, since it is enabled, this will be written into the parity bit. It will be stored in the 9th bit of the DRAM. So this is generation of the parity bit. As soon as the data is given, and you are giving memory write, I becomes 0 because of memory read becoming 1, and total I effect is not there, only the even number of ones are counted and even goes high, and that is written into the parity bit. Now let us read it. When you are reading, you have to read from the DRAM location. If you have to read from the DRAM location, the 9th bit, once again here the memory read is activated, and once the memory read is activated, the parity bit is now returned into I here. And what we have stored I equal to 1. Because previously it is the parity that is being generated is even parity, and so that 1 whatever has been returned will come here, and the data is still even, so even plus 1 here will generate the odd signal, and this odd signal is given to 7474. So this is your odd signal, and this odd signal is given to this 7474 through an inverter. It's given through an inverter. So the odd is generated, it becomes 1, and the D becomes 0, and the Q also becomes 0. If the Q is 0, then there is no error. If there is an error here, instead of an even parity, one of the bits has changed and it gives an odd parity. This odd plus whatever is stored is 1, it is there. The odd will not become high, it will become low, and this low, when it is transferring here inverted, it becomes 1. Once D is 1, Q also becomes 1, and the Q is connected to PCK, that is parity check, and this parity check is given to NMI, non-maskable interrupt, and this will generate the error signal. So this whole combination will act as a parity generator and checker, which will generate the error message if there is an error. So this is the end of today's class. So before we go, just winding up, when we have the 640K RAM, which we have seen with arranged as 8 bits, that is 64K and 256, you can still make it as 16 bits. So for 16 bits, what do we do? D0 to D7 and D8 to D15. So can you see that 4 64Ks are there? Arrange 4 64s together, and again 4 256 are there. 256Ks you arrange in a line. So each one, this is 4 bits, 4 bits, 4 bits, 4 bits, totally 16 bits. For every 8 bits, 1 byte, you add a parity. So these parities are distributed like this. So this gives me the arrangement of DRAM as odd and even banks. So you can, the same circuit that we have used previously can be used for the parity checking of the word location also. So thank you.